Hey everyone, welcome to your Geometry Play Pause It for the week. We're going to be covering the last lesson that occurs in Unit 1, and that is the applications of triangles and the Pythagorean theorem. So go ahead and grab your notes, have that Play Pause It graded assignment open, and we'll get started. The first thing I'm going to show you guys is a quick-ish video. And this is showing a few different ways to prove the Pythagorean theorem. So sit back and relax, and then we're going to talk about it.
What do Euclid, 12-year-old Einstein, and American President James Garfield have in common? They all came up with elegant proofs for the famous Pythagorean theorem, the rule that says for a right triangle, the square of one side plus the square of the other side is equal to the square of the hypotenuse. In other words, a squared plus b squared equals c squared. This statement is one of the most fundamental rules of geometry and the basis for practical applications like constructing stable buildings and triangulating GPS coordinates. The theorem is named for Pythagoras, a Greek philosopher and mathematician in the 6th century BC, but it was known more than 1,000 years earlier. A Babylonian tablet from around 1800 BC lists 15 sets of numbers that satisfy the theorem. Some historians speculate that ancient Egyptian surveyors used one such set of numbers, 3, 4, 5, to make square corners. The theory is that surveyors could stretch a knotted rope with 12 equal segments to form a triangle with sides of length 3, 4, and 5. According to the converse of the Pythagorean theorem, that has to make a right triangle, and therefore a square corner. And the earliest known Indian mathematical texts, written between 800 and 600 BC, state that a rope stretched across the diagonal of a square produces a square twice as large as the original one. That relationship can be derived from the Pythagorean theorem. But how do we know that the theorem is true for every right triangle on a flat surface, not just the ones these mathematicians and surveyors knew about? Because we can prove it. Proofs use existing mathematical rules and logic to demonstrate that a theorem must hold true all the time. One classic proof, often attributed to Pythagoras himself, uses a strategy called proof by rearrangement. Take 4 identical right triangles with side lengths A and B and hypotenuse length C. Arrange them so that their hypotenuses form a tilted square. The area of that square is C squared. Now rearrange the triangles into 2 rectangles, leaving smaller squares on either side. The areas of those squares are A squared and B squared. Here's the key. The total area of the figure didn't change, and the areas of the triangles didn't change. So the empty space in one, C squared, must be equal to the empty space in the other, A squared plus B squared. Another proof comes from a fellow Greek mathematician, Euclid, and was also stumbled upon almost 2,000 years later by 12-year-old Einstein. This proof divides one right triangle into 2 others and uses the principle that if the corresponding angles of 2 triangles are the same, the ratio of their sides is the same too. So for these 3 similar triangles, you can write these expressions for their sides. Next, rearrange the terms. And finally, add the 2 equations together and simplify to get AB squared plus AC squared equals BC squared, or A squared plus B squared equals C squared. Here's one that uses tessellation, a repeating geometric pattern, for a more visual proof. Can you see how it works? Pause the video if you'd like some time to think about it. Here's the answer. The dark gray square is A squared, and the light gray one is B squared. The one outlined in blue is C squared. Each blue outlined square contains the pieces of exactly one dark and one light gray square, proving the Pythagorean theorem again. And if you'd really like to convince yourself, you could build a turntable with 3 square boxes of equal depth connected to each other around a right triangle. If you fill the largest square with water and spin the turntable, the water from the large square will perfectly fill the 2 smaller ones. The Pythagorean theorem has more than 350 proofs, and counting, ranging from brilliant to obscure. Can you add your own to the mix? Did you enjoy this lesson? If so, please consider supporting our nonprofit mission by visiting patreon.com/TEDEd.
All right. So which proof stood out to you the most? Which one made the most sense to you? For me, I have always loved this one, the water fill one, where you're looking at the volume essentially of the larger square equaling the smaller 2. There are a few here I had never seen before. This one, and in fact, this might be my new favorite just because it relates to so much that we've been doing lately with similar triangles. The algebra gets a little clunky or complicated, but if we sat down, you guys could definitely work through this. But it's just not something you've probably done in a little while. But I thought that was neat seeing those proportional sides with those similar triangles. So hopefully by now you're convinced that the Pythagorean theorem is true and always works. We are going to do a few examples together in our notes of using the Pythagorean theorem. So just to kind of recap what those videos were showing, when you have any right triangle, you can take, let's review, these are called, basically you have 2 sides here. This is a side, this is a side, and the side across from the right angle is always the hypotenuse. It is the longest edge of that right triangle. So the Pythagorean theorem says you take a side squared plus the other side squared, and it will always equal the hypotenuse squared. So the big deal here is that on the right-hand side of that equal sign, you always want to have the hypotenuse. No matter how the triangle is oriented, you know, we'll see some where they're kind of turned and twisted. As long as you go across from that right angle, that is the C value. That's the hypotenuse. So let's try one. Here's an example. In the following figure, A is 3, B is 4, and C, find C. We don't know what C is. All right, so we're going to basically plug these values into the Pythagorean theorem. A is 3, B is 4, and we don't know C. So I'm just going to leave it as C. You know, you can make it anything you want, X, Y, Z, whatever, any variable. So now we get to use our algebra. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. Now, do you remember back from algebra how to get the C by itself? What is the inverse of squaring? The inverse, or the opposite operation of squaring, is taking the square root. So if we take the square root of both sides, just to kind of show you here on the right-hand side, this kind of expands out to C times C. Now remember, when you have a pair of things, it comes out. It gets rid of the square root. So that's why these are inverses of each other. These will cancel out, and you'll just have C. And the square root of 25 is plus or minus 5. Remember, you always have that positive answer and the negative answer. And if you don't believe me, let's look up here. 5 times 5 is 25. There's the positive answer, the positive 5. And also, check out negative 5 times negative 5. That is also 25. So we also have the negative answer. That's why you're always going to have a plus or a minus. But you want to look at the context of your problem. We're talking about the length of a side of a triangle. You guys think we'll ever have negative length? The answer to that is no. You might go in a negative direction, you might walk backwards or down, and that's sort of in a negative direction, but the actual distance and length that you travel or that something is measured is always positive. So C is 5. And something that you may have caught on to by now, maybe you've seen the Pythagorean theorem, or you will see this, is that this is actually a very special right triangle, a 3, 4, 5. There's a bunch of these. And you saw a list of them, I think it was from the Babylonian stage. They had a bunch of those special right triangles. They're called Pythagorean triples. And you won't need to memorize those because you can always figure them out. So let's try a bunch. Remember, you can always pause this recording at any time, try them on your own, and then come back for the answer. So question number 1, we're going to be using the Pythagorean theorem for all of these because these are right triangles. You can only use the Pythagorean theorem on right triangles. Doesn't work on any other kind of triangle. So the first thing I always like to do is find C. Remember, that's across from the right angle. So this is C. And then it doesn't matter what you use for the other ones. So I'll just do 12 squared plus x squared equals 13 squared. So this time we're solving for one of the side lengths. So we get 144 plus x squared equals, I think this is 169. Did you guys ever memorize your squareds like that? I'm just going to grab my calculator. Yeah, it is 169. All right, so we're going to try to solve for x. We're going to get x all by itself. So I'm going to move the 144 over by subtracting it. That's the opposite of the positive 144. And you get 25. So to get x by itself now, we do the inverse of squaring, the opposite of squaring. Remember, that's square rooting. And the square root of 25 is plus or minus 5. And we know that it's going to be positive 5. So x is 5. So whenever you have a triangle, because one of the side lengths is 5 and one is 12, the other one will always be 13. This is another special 5, 12, 13. Let's try number 2. Here is C. You probably could already guess. Look, we have 3 and 4. What's it going to be? It's going to be 5. It's a special right triangle, a Pythagorean triple, but we can always solve for it. So 16 plus 9 equals C squared. This is 25. To get rid of this squared, we take the square root of both sides. Those are the inverses, so it cancels, and you get 5. All right, let's try number 3. I just want a different color. Change it up a little. All right, here's where the triangle's turned. But look, there's that right angle. So this is the C value. So the other two numbers are the sides. We have some decimals here, which is totally fine. Actually, it makes more sense that you're going to have decimals in the real world, but you probably want your calculator. So I got 141.61 and whoops, 216.09. All right, now we're going to keep solving for x. I'm going to subtract 141.61 from both sides. And I'm going to come over here. We have x squared equals 74.48. So we'll just take the square root of both sides. Take the square root of 74.48. And it does tell us to round our answer to the nearest tenth if necessary. So I got 8.6. And of course, we know that it's going to be the positive value because you can't have a negative length. All right, the last one on this slide. Here's our C value. So 6.3 squared plus x squared equals 15.4 squared. So your missing value can either be a side length or the hypotenuse. And it does kind of change a little bit on how you solve them, right? Depending on what's missing. And this is just some calculator work. 15.4 squared is 237.16. And I'll subtract 3969 from both sides. X squared equals 197.47. And I know you guys are trying these along with me. X equals plus or minus. Oops, I accidentally put 297. That's not going to work. 14.0. Nope, 14.1. And X is the positive 14.1. All right, so that was just basically plugging those values into that formula and being able to solve for the missing side length. So let's see it apply to some real world applications. So here is an airplane coming in for landing, and this is the flight tower. And the flight tower, the airplane has a lot of very high tech devices on it that are able to give the flight tower and also the pilot different measurements and heights and speeds and all of that. And so I don't know any of the flying technical terms. I have flown on a plane before. But, you always hear things like, we're descending at so many feet per second and things like that. So we know just how much, even just from seeing movies or maybe flying on an airplane, how much math is involved in the technology that you find in airplanes. So let's see the distance here, this diagonal distance from the plane to the tower here. So we're going to call this C. Now it's not labeled 90 degrees. So ideally there would be some more information in this problem. It would say something like the vertical height to the airplane is perpendicular to the ground. That would be some clues to tell you, right? Perpendicular to the ground, meaning that it forms a 90-degree angle. So let's just use these big numbers. The trick, not really the trick, but the whole deal with the Pythagorean theorem is just making sure you put the numbers in the right place, making sure that that hypotenuse is always on the right-hand side of the equal sign. And I'm going to grab my calculator on this one. I probably could leave the zeros out and then add them back in at the end, but kind of fun to see them all there too as well. Whatever you guys want to do. I'm going to leave those out. That's a lot of zeros. Mm, 2.5 billion, I think. All right, and then we'll take the square root of both sides. All right, x is plus or minus 50,000 feet. And we are descending, but it's still not a negative number. It's still going to be that positive 50,000 feet because we're talking about a distance. Now you might hear pilots use words like descent and negative, like a angle decline, angle of depression here, and things like that. We're going to talk about angles of depression and angles of elevation a little bit later. All right, here's another example. Find the height of the building at the top of the ladder. So my stepdad is a firefighter, and actually he retired last year as a battalion chief. So, I mean, yeah, he was a battalion chief, but he didn't really get into the fires anymore recently. He is retired now, but he told me that they actually use the Pythagorean theorem to decide which ladder to grab off the truck. And I was like astonished. So, of course, as they get into their industry and their field and they do it enough, they don't have to sit there and do these calculations. They know what's going on and they know the buildings in their communities. But he said while they're training and scoping out the neighborhoods, they definitely do use math. So this one, they give you the length of the ladder. So ideally, what he told me that they do is that they know the height of typical stories in a building. So like this is a 3-story building. So they would know that typical height and be able to decide how far away to put the ladder to reach which window. Like if the person was in this window and they needed to save that person, they knew that person was on the third floor of that three-story building. And I actually don't know the height of a three-story building. I guess we're going to find out when we solve this approximate height. Then he knew he would need to grab the particular ladder and place it that many feet away from the building so that it would meet the window, which I thought was just crazy cool. So we're going to do one of those. This is just an example. It might not be the building that he has fought fires in. We have x squared plus 5 squared equals 13 squared. You might recognize this triangle already as a special triangle, but let's solve it. So 169 minus 25, right, is 144. And then we'll take the square root of both sides because that's the inverse of squaring. And you get x equals 12 feet. So in this case, whoops, 2 stories of this building are 12 feet. So each story is about 6 feet approximately. So he would know, I'm going to grab that 13-foot ladder and I'm going to put it 5 feet from the base of that building to reach sort of the tip of that third floor. Because when you're dealing with life and death and fire, you don't want to have to waste any time. You don't want to have to grab a ladder, put it up to the building, and you're like this, and you're like, oh man, that's not long enough, or it's not the right angle. And you get another ladder and you put it, you try to change the angle, but it only reaches to the second flight. So, I mean, you don't want to be making those decisions in that moment. So they do training and they do mathematics and they do practice and have sort of some generalizations for different buildings. So I thought that was cool. So now we're going to apply some of what we just learned in finding the area of a triangle. So here's the formula for area of a triangle. It's on your formula sheet. You guys, if you didn't know this, you get to use your formula sheet in this class whenever you want to on any test or quiz. Your original formula sheet, don't write anything on it. And then also you'll get your formula sheet on the SOL. So you will have this formula given to you. You don't have to memorize it. And the A stands for area. The little b is the base, and the little h is the height of the triangle. So let's practice a little bit here. This one, they give you the area. So let's write our formula up here. Area is 1/2 base times height. I just copied it from here. See? So we know the height is 18 feet. This is h. We don't know the base. That's what it wants us to find. And we know the area. So we're going to plug in what we know. Area is 180. We don't know the base, and the height is 18. So, I mean, like 1% of this problem is geometry in the sense what we had to recall the area of a formula, area of a triangle formula. But once you get here, it's just algebra. We want to solve for b and get b by itself. So let me grab another color. So there's a few ways to do this. On the right-hand side, let's go ahead and sort of combine anything that we can. This is all multiplication. So let's do 1/2 times 18. 1/2 times 18 is 9. That looks a little better. Now to get rid of the 9, this is 9 times b. So the inverse of multiplication is division, or the opposite of multiplication. And now we're going to divide. 180 divided by 9 is 20. And our units are feet, so we found the base is 20 feet. So this is sort of just some like formula manipulation. They're giving us some values and they want us to manipulate the formula to find the other values. So here again, they give you area. So area is 25. The base is 5. Now you might look at this diagram and you're like, hey, what's up with this dotted lines here? That's at the base, and that is not part of the base. The base is only the solid line of the triangle. These dotted lines are sort of mapping out where you can get to the height. Because the height is from the tip to the base. So to find it, you're not going to be able to just go like this. That's not the height. No, that's not the height because that's not how tall the triangle is. It goes all the way up to here. So that's not the height. So that's why you often see them extending the base out with these dotted lines to get you to that tip of the triangle. The base is only the solid line part. So the base is 5, and we're looking for h. All right, half of 5 is 2.5. And now we're kind of in the same place, right? We're just going to divide both sides by 2.5. And you get 10. And we're talking about yards. The height is 10 yards. All right, here's the last one for our play posit, and it's a challenge. So the area of a right triangle is 210 square inches. So you can write it as square inches. The same way you would write that with a label is just like this, inches squared. Remember, area is always squared. For example, the area of a square, let's say this is 3 feet, 3 feet. You're doing 3 feet times 3 feet. So it's 9 feet squared. 1 foot plus 1 foot. You always have squared when you're talking about area, any kind of area. The height of the right triangle is 35 inches. What is the length of the hypotenuse? Ooh, so let's draw it. That would be helpful. And I have to say, that's a pretty good free-handed right triangle, considering. So the height is 35. The area is 210 square feet. What is the length of the hypotenuse? So we're looking for this. We also don't know the base. Let's call it B. We don't know that either. All we know is that the area is 210 on the inside. So what could we use? Since we know the area, let's use the area formula. You might look at this and say, oh, I'm going to use Pythagorean theorem. Yep, they want to know the hypotenuse, so I'm going to use Pythagorean theorem. I'm ready. But when you go to do that, watch. Let's set it up. B squared, look, you have two unknowns. We don't know the base and we don't know the hypotenuse. So there's no way to solve that yet with two unknowns. So let's use what they give us, the area and the area formula, to figure out one of those unknowns. Look, we can find B. So the area is 210, base is, we don't know, and the height is 35. So let's solve for B. So half of 35 is 17.5. Now we'll just divide both sides by 17.5. And you get 12. So the base is 12. Now, look, now we can solve for the hypotenuse because we know the base. I don't really know why I put that in parentheses. You don't have to. All right, let's solve for the hypotenuse. This is 1225 plus 144. I'll just add those together. Now remember, the inverse of squaring is square rooting. So we're going to square root both sides, and you get 37. I never would have guessed that. Plus or minus, right? But because it's the length, again, it is going to be the positive. So it's 37 inches. Our units are inches. One thing I should mention, and I feel like I say this a few times, but just be cautious and careful of the units that they're using in the problem. Sometimes they will go tricky on you and they'll put two different types of units in the same problem. And before you can work with those numbers, you need to make the units match. Like they could have said here that the area is in inches, and they could have given you the height in feet. So you would have needed to convert that to inches. So just be careful. I'll try to pull some of those for us for next time, just so we can practice through that. Just make sure that all of the units match so you can work with the numbers. Challenge accepted and complete. All right, you guys, I will see you on Thursday. Please reach out if you have any questions at all, and I hope you have a great week. Bye, everybody.